All right, Precalculus, let's do this. Let's continue our journey. Today's game plan is to learn the proper definition of a polynomial. So if I feel like you've heard this so many times, you've seen this word, but if I said, hey, what does it mean for us to have a polynomial and what is a polynomial, how do you think you could describe it in your own words, right? Or how could you show it? So if you want, pause the video and think about it. And the idea for us today will have a proper definition for this. Okay. Here, how can we define a polynomial? So the definition might seem very intense or a lot, but once we go through the details of it, it's not too bad. So what I'd like you to do is, before we even read the definition ourselves, please have the definition down, and also have this part down as well, over here. Okay, so you could pause the video for this part here with the definition. So you could pause here, and then you could also pause here to have this down as well. Okay, so let's say you paused the video, you wrote it down. Let us begin. Definition of a polynomial function. Let n be a non-negative integer, and let a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers. A sub n does not equal 0. The function given by is called a polynomial function of x with degree n. So what on earth did you just read right now? When we think of a polynomial, you just have to think it's an expression with constants, variables, and or exponents that can be combined using plus, minus, multiplication, and division. What you're not allowed to have in a polynomial, you're not allowed to divide by a variable. A variable's exponents can only be whole numbers. So you could have 0, 1, 2, 3. We won't have any negative exponents for the variable. And you can't have an infinite amount of terms. So let's see, what on earth are we talking about here? We'll play a little game. It's a very fun game. The game is called Polynomial or Not. Right? So here are some examples of what you may think to be a polynomial or not. But the idea is, pause the video, and based on the definition and criterias of what constitute as a polynomial, which one of these are polynomials and which ones are not. Okay? So pause the video and try your best to think about it, and we'll go over each one. Okay? So here, let's look at the first one. Is this expression a polynomial? Yes, it is. Here we have our variable x. It's being squared. And actually, let me zoom in a little bit. We have our variable x. It's being squared. It's being multiplied by 3. You're adding 5. There are none of the criterias where it is not a polynomial are evident here. So we have this. This is okay. We have a polynomial. 5x over 2 plus 3. That's fine. This is a polynomial, right? We're taking x and we're multiplying it by 5 over 2, and we're adding 3. Life is okay. Here, if I have, let's say, 3 over 2x plus 5, is this a polynomial? This is not a polynomial, because here within this expression, you're dividing by a variable. And notice that here, you're not allowed to divide by a variable. So then here, for question 3, this part over here, this expression is not a polynomial. What about over here, question 4? This part is okay, but when you take a look at this part over here, because you have a negative exponent, we didn't talk about it in the course, but what will x to the negative 5 be? It will be 1 over x to the 5. And notice that by having a negative exponent, you're going to be dividing by a variable, and this is no bueno. So here, this is not a polynomial expression as well. Okay, let's take a look at question 5. This one was a fun one. So this is x plus x squared plus x cubed plus x to the fourth plus, notice that here with the ellipsis, the pattern continues. Is this a polynomial? This is not a polynomial because you have an infinite amount of terms because the pattern keeps continuing. And notice that is one of the criterias within what you can't have as a polynomial. You can't have an infinite amount of terms. And by generating this ellipsis pattern, you generate an infinite terms, so this expression is not a polynomial. Okay. What about just the variable x? This is fine. This is a polynomial, right? If I just had the number 1, this is a polynomial. This value over here, x to the negative 1, this is not a polynomial because you can't have a negative exponent. And here, this one was a little bit of a trick question. This is a polynomial because it's not okay, like, it's okay if the coefficient or the value to the left, I'm sorry, the coefficient could have a negative exponent, but the variable cannot have a negative exponent because what is 7 to the negative 2? It's really just 1 over 7 squared, which is equal to 1 over 49. So that's just, it's 1 over 40. Like you could translate this to this. And this is okay. You could divide by a number, you just can't divide by a variable. All right. Hopefully you had fun playing this game. So to be a polynomial or not, right? That was the first half of the lesson. The next half, which isn't too bad. Let me make sure I get the right worksheet I created for us, or the right notes. Okay. So here, that is algebraically how polynomials are shown. Here, what I'd like you to do is take a second, have this in your notes, right? And I'll zoom in. For polynomial functions of higher degrees, we have this part. You could pause the video. This part over here. Pause the video, please have it in your notes. Right. Okay, so let's say you pause the video and you have it in your notes. Polynomial functions of higher degrees. Visually, polynomial functions have continuous graphs. So notice that there are no holes within the graph, right? Notice that the function, this word of continuous becomes better, or you really learn what this word means of continuous within calculus. So the idea of a continuous function means that I could go through the function and not pick up my pen as I'm drawing the function. Here, functions with graphs that are not continuous are not polynomial functions. So here, if I take a look at this graph, it is not continuous, so there is no polynomial that will generate this visual. You would need a piecewise function to create this visual. So this is not a polynomial function. Here, polynomial functions have graphs with smooth, rounded turns, right? So the turns within a polynomial will be smooth. They will never have this V-ish shape like within an absolute value x. That's not possible for a polynomial function. So graphs of polynomial functions cannot have sharp turns. Okay, so far so good. Now the final part of the lesson, this will be a very short lesson, is the idea of end behavior of a polynomial. So here, what are we talking about? If I had, for example, let's take a look at this one here. Well, actually what I'd like you to do is, please have this in your notes, right? Try and create this, right? Have 4 sections within your notes, right? And for each section, we'll have, it should just look like this for each one. You're basically creating 4 of these, where we'll talk about the degree, the leading coefficient, the end behavior, and what's happening as the graphs go towards positive infinity and negative infinity, okay? So create 4 of these, and let's say you did, and now you want to go through the lesson here. Okay, so here we have end behavior of a polynomial. So if I had an example such as, let's take a look at x squared. What does x squared look like? It'll have, let me get the correct color pen for us. Okay, I like this baby blue. Let's rock with this baby blue. What does x squared look like? It looks something like this, right? That is x squared. If I have a polynomial such as, let's say, x to the 4th, or let's say x to the 10, notice that if my exponent is even, or my degree is even, and my leading coefficient is positive, right? Like the value to the left of the variable, if this is positive, then we will always have this similar end behavior, stating that as x goes to infinity, right? So you see here, this is x is 1, x is 2, x is 3. You see, as x is approaching positive infinity, what is happening to the y value of the graph? Notice that as x goes to infinity, what is happening to f of x? This is also going to positive infinity, right? You see, as x is getting very, very large, my y value is also getting very, very large. Here, what about if we go towards negative infinity? As x approaches negative infinity, what is happening to my f of x value? What's happening to the graph as I get closer and closer to negative infinity? The graph is going up to positive infinity. And that's how we will have it. This will always happen for any polynomial function where the degree is even, right? The highest degree is even, and the leading coefficient is positive. So what would be some other examples that have this similar end behavior? What if I had x to the 6th plus 5x to the 5th plus 4x cubed plus 7x squared plus 2x plus 1? This polynomial function, as large as it is, we know that the end behavior of the graph for this polynomial function will have this behavior. Whatever this graph looks like, I know as x approaches infinity, my f of x will also go to positive infinity, and it will have this visual. Let's look at another one. Imagine if I had same idea. Let's say if the degree is even, but my leading coefficient is negative. So what are some examples of graphs like that? What if we had something like negative x squared, or negative x to the 4th, or negative x to the 10th, or even negative x to the 1000? Notice that if the degree is even and my leading coefficient is negative, then visually the graph will have an end behavior that looks like this. We don't know what's happening here, but we know towards negative infinity and positive infinity, the graph will have to look like this. So then how would you show the end behavior for this? Just like we did over here, right? So take your time, pause the video. As x is going to infinity, what is happening to my f of x value? As x approaches negative infinity, what is happening to our f of x value? Right? Pause the video and think about it, right? Here, let's say you pause the video, right? This is 1, this is 2, this is 3, right? As x is getting closer to positive infinity, what is happening to my f of x value? It's going down to negative infinity. What about here? As x is approaching negative infinity, what's happening to our f of x value or the y values? It's also going down to negative infinity. This will always occur if the degree of the polynomial is even and the leading coefficient is negative. Okay? All right. Well, notice we talked about even degrees. What about if my degree is odd? So if I had an example such as, let's say, x cubed, or I don't know, 10x to the 5th plus 4x to the 3rd plus 2x squared, right? Notice that when we take a look at this polynomial, when we take a look at these polynomials, the degree is odd, right? The highest exponent within the polynomial is odd, and the leading coefficient is positive. So if I said pause, what does x cubed look like without looking at your notes, how do you show x cubed? Right? Should look something like this. What I'd like you to do is show the end behavior. How would it go, right? As x approaches infinity, what's happening to my f of x value? As x approaches negative infinity, what's happening to my f of x value? Be patient, take your time. Right. Here, as x is going to positive infinity, your f of x is also going to positive infinity. As x is going to negative infinity, your f of x is going down to, oh, I'm sorry, there's a typo here. That should be negative infinity. Okay. Last one. We've done even positive, even negative, odd positive, final one, odd negative. I feel like if you feel like you're good, why don't you try it by yourself? Without even looking, pause the video and try and do what you think I'm going to write. Okay, you got this. What are some examples, right? Negative x cubed, negative x to the 7, right? What will this graph look like? Something like this, right? What would be the end behavior? As x goes to positive infinity, f of x will go somewhere. As x goes to negative infinity, f of x will go somewhere. Okay. Here, x is going to positive infinity. What's happening to the graph? It's going down to negative infinity. As x is going to negative infinity, the graph is going up to positive infinity. And that's it. That's the lesson. What I'll do is, on Delta Math, I'll give some nice questions that will help reinforce this concept and material, and we'll go over it together in class. Hope you enjoyed it.